Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. For tonight, we're going to continue our exhaustive review of the chemical elements. In part 1, we ended with element number 12 in the periodic table, magnesium. Our next element is aluminum, which is number 13. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project, get more of it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. You will gain access to 25 exclusive episodes, and we add a new one every month. And you can listen and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon, as well as links to different streaming options, which may be better suited for you. You will find them in the description of the podcast. And now, before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries. Assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath. And when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, off we go. So let's begin with our first element tonight. Element number 13, aluminum. As you remember from part 1, this means that it has 13 protons in its nucleus. We are all rather familiar with aluminum because it is quite present in our daily lives, in plenty of appliances and cars, in metal cans for drinks. You may have noticed that it is also very lightweight for a metal. It is not very dense, and we will see why. In the previous story, I told you about families or groups of elements that are presented vertically in the periodic table of elements. And the elements within these groups share some of their properties when it comes to their propensity to associate with other elements to form molecules and compounds. These properties are strongly determined by their number of electrons. When they associate with others, atoms try to fill, to saturate, their outermost layer of electrons. This makes them strongly inclined to look for the few electrons they miss, or to give away one or two. It makes them more or less prone to react with other elements, or less prone to react with other elements. Elements of the same group, of the same family, have the same number of electrons to give away or to acquire. This is why they share some of their properties with others from the same family. Aluminum is in the family of boron that I told you about already. This boron family forms compounds primarily with oxygen. It bonds very easily with it. This is the reason why, on Earth, aluminum is almost never found in nature as a free element. It almost always occurs as an oxide in association with oxygen. So there is a lot of aluminum in the Earth's crust. It is even the third most abundant element there, after oxygen and silicon. But it almost always comes associated, not alone, in particular in a type of rock called bauxite. Bauxite is a kind of sedimentary rock that is often reddish-brown, but it can also be white, and its composition can vary. It is rich in aluminum and contains different types of aluminum oxides. Typically, the way to extract metal is to mine ore, for example, iron ore or copper ore. Ore being a general term for compounds that are rich in one or several metals, because in nature, metals are almost never found pure and alone, separated from other elements. For most common metals, this ore is smelted in a furnace shortly after extraction, if it is rich enough, or if it is not, after a first treatment. During this process, unwanted elements are eliminated. They are separated from the metal, which emerges pure or almost pure from the process. In the case of aluminum, things are a bit different. The ore is bauxite, and it is not smelted, but rather treated chemically and electrically. First, aluminum oxides are extracted because bauxite contains other elements that are unwanted. This gives alumina, which is pure aluminum oxide, and this alumina is treated electrically. It consists of aluminum plus oxygen. So the goal is to separate these two elements and collect only pure aluminum. This is achieved with electrolysis, the separation of elements using electric current between two electrodes. In the case of aluminum electrolysis, one electrode is made of carbon that serves as an alternative pairing to oxygen atoms. After they separate from aluminum, they bond with carbon to make carbon monoxide or carbon dioxide. This gets rid of the oxygen, and pure aluminum can be harvested in this way. Aluminum has different things, different aspects that make it appealing. It is relatively easy to work with. The abundance of bauxite makes it accessible. It is not a rare element. I told you before that it is the third most abundant in the Earth's crust. It is also lightweight for such a strong material. So aluminum has appeal, and indeed it has many uses, but it can be relatively expensive to produce because it requires a lot of electricity. An aluminum plant can consume as much electricity as a small city. This is why traditionally, since this production was discovered and industrialized in the 19th century, aluminum plants have been built near cheap electricity sources, like dams that produce hydroelectric power. The production of aluminum also has a significant environmental cost because of the energy required, first, and also because of the release of carbon dioxide as a byproduct. But still, aluminum is very useful when strength and lightness are required, for example, to make aircrafts. Since the rise of modern aviation, planes have used a lot of aluminum parts. It is also used for packaging, for example, in cans for beer or soda. But why is aluminum so light in comparison with other metals like iron? There is not one, but rather two reasons for it. The atomic mass and the way atoms are arranged. So first, the atomic mass. A nucleus of aluminum always has 13 protons. The most common isotope of aluminum has 14 neutrons. So that makes 27 particles in the nucleus. Iron typically has 56 particles in its nucleus. So one iron atom has about twice the mass of one aluminum atom. On top of that, the way aluminum atoms are arranged under atmospheric conditions on Earth leaves more voids between them, more space. So it takes about 1.5 times more atoms to fill the same volume. Between the lower atomic mass and the smaller number of atoms, these are the reasons why aluminum objects like ladders or cans feel so lightweight in comparison with iron or steel. They require fewer atoms, and on top of that, these atoms have about half the mass. In total, the density of aluminum is about 1/3 that of iron. Our next element is another one that is very present in our daily lives: silicon, number 14. I told you before that silicon was the second most abundant element in the Earth's crust after oxygen. Silicon alone represents about 28% of the mass of the Earth's crust, and in association with oxygen, it forms compounds called silicates, which are also commonly known as rocks. These minerals, the silicates, represent about 90% of the Earth's crust, and in the same forms associated with oxygen. Silicon is widely distributed throughout the universe in cosmic dust, asteroids, and rocky planets and satellites. It is the 8th most abundant element in the universe. I told you that silicon was extremely present in our lives, and this from prehistoric times. Many building materials and materials used for crafts contain clay, sand, or stone. Since silicon is a major component of sand and rock, it also ends up in cement and concrete. So we find it in our houses and our roads. Glass is also made primarily from silicon. There are different possible compositions for glass, because glass is the name given to a type of solid that is often transparent and chemically amorphous. Amorphous in chemistry means that if you look at it even on a microscopic scale, the atoms it is made of are not ordered. They are not arranged according to a pattern, but instead form a randomly arranged mass, hence the term amorphous, which suggests that there is no shape, no pattern to it. So in chemistry, an amorphous solid is the opposite of a crystal. A crystalline structure is one in which there is a periodic arrangement of atoms that repeats itself. the exact opposite of an amorphous structure. That can be a bit confusing because in everyday language, glass and crystal are sometimes considered almost the same thing, and they can look the same. But if we look more closely at their structure, they are very different. Yet another frequent use of silicon is silicones, which are very large molecules, and there are different sorts of silicones with different properties. But what they have in common is that they contain a lot of silicon atoms, together with other elements we already reviewed, like oxygen, carbon, and hydrogen. Silicones are used in a lot of things, in sealants, lubricants, adhesives, insulation, and cookware. Yet another critical use of silicone is in electronics. Highly purified elemental silicone is essential for making the transistors and chips that are used in electronic devices, computers, smartphones, onboard electronics in cars, and home appliances. All of these could not function without silicone. The property of silicone used in these applications is that it is a semiconductor, which, as the name suggests, means that it can conduct electricity, but not always, or not perfectly. A semiconductor falls somewhere between an insulator, for example glass, we just talked about, and a conductor such as iron or copper. Silicon is also an important element in biology. Not so much for larger animals. Only traces are present in our organisms, but it is present and necessary in small quantities in many plant tissues. There are also different microorganisms, microscopic algae, and animals that use it to build a kind of tiny skeleton for themselves. Element number 15 is phosphorus, yet another critical element for life. When I told you about nitrogen in the previous part, I explained that nitrates were important for plant growth and used in fertilizers. So are phosphates, which are compounds that contain phosphorus. Phosphorus is not a very rare element. In 1 kilogram of the Earth's crust, there is about 1 gram of phosphorus. But it is very reactive under normal conditions, and this is why it is never found as a pure element on Earth, as a free element. Pure phosphorus under normal conditions can have different forms, different allotropes. You remember that an allotrope is a different arrangement of the same atoms that can give an element a different appearance and different properties. For example, graphite, also known as pencil lead, is chemically identical to diamond. Both are pure carbon, but the atoms are arranged differently. Pure elemental phosphorus also comes in 2 major forms, 2 allotropes, white phosphorus and red phosphorus. You know the term phosphorescence, which is used for things that glow after illumination. It actually comes from phosphorus because it was observed that white phosphorus emitted a faint glow when exposed to oxygen. This glow is produced by the oxidation of phosphorus in its white form. It doesn't happen with red phosphorus. The correct term for this phenomenon should be chemiluminescence. Nowadays, the term phosphorescence refers to a different process that is independent of phosphorus. It's a bit confusing, but historically, The term phosphorescence appeared because of the glow of white phosphorus. Our next element, number 16, is sulfur. Under normal conditions, sulfur is a solid and looks like yellow crystals. One particularity is that sulfur atoms tend to group in eighths under these conditions, forming molecules with 8 atoms. Sulfur was one of the first elements to be identified because it is relatively abundant. It was known in ancient times from China to the Mediterranean. Nowadays, a lot of sulfur is obtained from the treatment of oil and natural gas when they are refined and stripped of unwanted components. Elemental sulfur is a frequent byproduct of the refining process. This covers the need of the chemical industry, which uses sulfur for fertilizers and to make matches or insecticides. After the elements that form the basic building blocks of organic life, like oxygen, hydrogen, and carbon, which are present in large quantities in our bodies, sulfur is another element essential to life. It is present in compounds that make up amino acids, proteins, and vitamins, and in keratin, which is the building material of our hair and nails. Many elements are necessary for organic life. In fact, apart from the very rare and heavy atoms that we will review later, we need dozens of different elements, many of them only in trace amounts. One of the few exceptions among those we have just reviewed is aluminum. It is not part of the biochemical functioning of any living being that we know of. After sulfur comes chlorine, with number 17. Under normal conditions, chlorine is a pale yellow or greenish gas, but it is extremely reactive, which is what makes it toxic in its gaseous form, but also explains why it is absent from the atmosphere. It reacted long ago with oxygen, nitrogen, or sodium to form compounds like table salt, which I told you about when we discussed sodium. In antiquity and the medieval period, salts containing chlorine were quite popular with alchemists because by heating and mixing them, they could perform spectacular experiments. For example, they could make a substance called aqua regia, Latin for royal or regal water. Aqua regia was a mixture of nitric and hydrochloric acids. First, it is a fuming liquid, so it makes an impression, but it also has the power to dissolve gold, which gave it an aura of magic. By the way, since we are in the Middle Ages, when were all these different elements we are talking about discovered? The way elements are classified has changed a lot in the past 2 or 3 centuries. Many different models emerged from the late 18th century to the 20th century. Prior to that, the nature of matter was a subject of much speculation from the ancient world to the Middle Ages. A common model was the belief that matter was made of a small number of basic elements: water, fire, air, and earth. In some cultures, metal or wood were also included. This conception was sidelined in modern times when the first chemical elements were identified. We know today what water, air, and fire are made of. They are not essential basic elements, but instead are composed of different atomic elements. Water is hydrogen and oxygen. Fire, if we consider only the flame, is primarily a mixture of carbon dioxide, water vapor, oxygen, and nitrogen, plus whatever elements the burning object may contain and release. Air, if we take the air around us, is mostly nitrogen and oxygen, plus a bit of hydrogen, because there is moisture in it, carbon, and traces of many other gases. Earth, as we have seen, varies a lot depending on where you take it from, but it always contains about 2/3 oxygen and silicon, plus many other elements. It can contain a lot of water too, if it's wet. So all these primordial elements that were thought to be the basic components, the basic bricks of matter in ancient times, are in reality combinations of other elements. The atomic classification of elements is something that emerged in the late 18th century. The first periodic table of the elements, resembling the one we know today, dates from 1913. At the time, it contained only a few dozen elements, far fewer than today. Today there are 118, because many of them had not yet been discovered. If we look at the timeline of the discovery of elements, out of these 118, only 14 were known in antiquity. These included many metals, iron obviously, copper, zinc, silver, gold, platinum, tin, and lead. We will review many of these metals later. 27 more elements were discovered between the Renaissance and the Age of Enlightenment, the 3 centuries from the 16th to the 18th century. That period could be called the time of scientific revolution. Most of the elements I have told you about up to this point are among them, with the exception of noble gases like helium or neon, which were discovered in the 19th century, and lithium too. The 19th century was like a golden age for chemistry. It started with 41 elements already known, and 42 more were isolated and identified during this century. It was also the time when atomic theory replaced older approaches and systematic classifications of the elements appeared. This productive period for discoveries in chemistry continued into the first half of the 20th century, when 14 more elements were named, including many naturally radioactive elements like plutonium or mendelevium. One thing that had changed by the beginning of the 20th century was the approach to searching for new elements waiting to be discovered. The fact that the number of protons in the nucleus is what makes an element what it is meant that there could only be one element with a given number of protons. One element with one proton, one with two, one with three, and so on. So as the periodic table was completed, chemists and physicists looked for elements with specific number of protons. Sometimes these new elements could be synthesized artificially. Some have been created that do not occur naturally. Among very large atoms with many protons and neutrons, they're often unstable. I will elaborate a bit more on these very large atoms as we approach the end of the periodic table, but some of them exist only in laboratories. It is always interesting to know that they are real and can exist, but they are not used for anything and cannot be found in nature. These have names most of us never hear, like oganesson, tennessine, or livermorium, and they were synthesized during the past 20 years by making some atoms collide in particle accelerators or by bombarding atoms with particles. So let's move on to number 18. Argon. Argon is a third noble gas after helium and neon, which we already covered. The name argon is derived from Greek, and it means lazy or idle, which is not surprising for a noble gas. Like the other members of this group, for the same reasons, it has very low reactivity. Argon is used for fluorescent lighting like neon, and also, due to its low reactivity, it is used in high-temperature industrial processes as a shielding gas or for welding. When temperatures rise, many elements become more reactive. They are excited by the available thermal energy around them. So this is when a noble gas comes in handy. For example, an argon atmosphere is used in graphite electric furnaces to prevent the graphite from burning, which would happen if it were surrounded by a normal oxygen-rich atmosphere. Number 19 is potassium, the third alkali metal after lithium and sodium. Chemically and visually, potassium is a lot like sodium. Under normal conditions, it is a white or silvery metal that is very soft. It can be cut with a knife, and it is very reactive. It reacts immediately with oxygen in the air. So as you now understand perfectly, this means it is not going to be found free and pure in our environment, but rather in minerals or dissolved in seawater. An essential role of potassium in our bodies is nerve transmission. Nerve transmission needs potassium ions. That is to say, potassium atoms stripped of electrons and carrying an electric charge. These particular ions can cross nerve cell membranes. This is why we absolutely need some potassium in our food. Fresh fruit and vegetables provide some. The name potassium actually reflects how it was traditionally obtained. It comes from potash, salts containing potassium that were produced by taking plant ashes, adding water, heating, and evaporating the mixture. This solution, potash, had different uses long before the Industrial Revolution. In ancient times, it already served to make soap or glass in ceramics and for bleaching textiles. It is an additive that has been in use for thousands of years. Element number 20 is calcium, another abundant element on Earth that we generally encounter as calcium carbonate, associated with carbon and oxygen. It is found in eggshells, in the shells of gastropods, and in pearls. When there are huge deposits of calcium carbonate in geological layers made from the skeletons of ancient marine life forms, especially plankton, it is because for millions and millions of years, the microscopic skeletons they made using calcium accumulated at the bottom of the oceans. They were compressed, and in different places like Western Europe, these layers of sediment later emerged. This is what chalk is made of, calcium carbonate. As you know, calcium is also a vital element for our bodies. It is known for its role in bones, but it goes beyond that. It is actually the fifth most abundant element in the human body, and it plays a role in the health of our muscular, digestive, and circulatory systems. It is involved in the formation and functioning of blood cells. We couldn't live without it. Now that we have passed element 20, we are going to start encountering less familiar and more mysterious elements. We still have a lot of well-known metals to talk about, from iron to copper and gold, and some of them are rather abundant. But we will also encounter other elements we rarely even hear about, like element 21, scandium. Scandium is part of a set of 17 elements that are often called rare earth metals or rare earths. Each of them has a few industrial applications, generally very specific ones, as additives in alloys, as components in electronics, or as catalysts in industrial processes. You have probably never heard their names unless you have a job that requires it. Apart from scandium, which is element 21, these rare earths, number 39, yttrium, number 57, lanthanum, number 58, cerium. Actually, all elements from 57 to 71 are part of this group. These different elements are found associated with one another and with other elements, other metals. So refining rare earth deposits is always necessary to extract them and obtain them in pure form. Demand for some of these rare earth metals has skyrocketed in the recent years due to the applications in electronics, such as LED lamps, screens, and electric vehicles. And at this point, China is by far the largest supplier in the world. So there is a scramble around the world at the moment to bring other rare earth mines and deposits into production, because these are strategic resources that could also become very lucrative in the coming decades. Element 22 is titanium, a metal that is found in nature only as an oxide, but can be purified and reduced to produce an element with a silver color. A relatively low density, it feels lightweight, but high strength and high resistance to corrosion. Strength is what titanium is best known for. When it is pure, it is as strong as steel, but less dense. Most of the time it is used in alloys with iron and aluminum when high-performance materials are required, for example in aerospace. It also serves as a catalyst. Titanium is denser than aluminum, about 60% denser, but more than twice as strong. So, looking at the ratio of its strength to its weight, it is a great choice as a high-performance material and, in various applications, a more upscale alternative to aluminum. Number 23 is vanadium, another metal that was discovered in the 19th century and also has this silvery gray appearance. It is mainly used in the production of steel and aluminum alloys. It was discovered at the beginning of the 20th century that a small amount of vanadium added to steel could considerably increase its strength. So since then, Many steel objects that need to be particularly strong, like gears, some bicycle frames, or crankshafts and engines, have been made of steel containing vanadium. Another element often added to steel is element number 24, chromium. You know about stainless steel, also called inox. This type, or rather this family of alloys, was developed when it was discovered that an amount of chromium, typically 10% or more, could make stainless steel resistant to corrosion. It no longer rusts. Chromium forms a coating, a passive film, that prevents damage to the metal. So chromium is very resistant to corrosion. It is also a hard metal by itself. Apart from stainless steel, another use is chrome plating, the creation of a thin film, a thin layer of chromium on metallic objects. You've seen the shiny parts of motorcycles or some cars. These are chrome plated because chromium is also very resistant to tarnishing. What we call tarnish on metals is, in fact, just a thin layer of corrosion that appears due to oxidation. It is not always oxygen, actually. For example, silver tarnishes in contact with air mainly because of hydrogen sulfide, a gas present in trace amounts in the atmosphere. So chromium does not tarnish, and it can be highly and durably polished because of this, which is why it is used mainly as a means to protect and embellish other metal parts. Element number 25 is manganese, yet another metal that serves in alloys. It often enters into the composition of stainless steel, too, because it improves strength and resistance to wear. It looks a lot like our next element, which is a big one, iron, number 26. Iron is a big deal. First, because it is, by mass, the most common element on Earth, just ahead of oxygen. There are more oxygen atoms, but an iron atom is about 3 times as heavy as an oxygen atom. So, by mass, an estimated 32% of Earth is iron, and oxygen represents 30%, a bit less. Most of this iron is in the Earth's outer and inner core, and its prevalence in the crust is much lower. It is only the fourth most abundant element in the crust. It is believed that a large part of the iron now found in the crust arrived during the late stages of Earth's formation. Iron is heavier than many of the elements that make up the bulk of the planet. So over millions of years, it tended to migrate towards the center of the planet, toward its core, which is believed to be very rich in iron. This did not leave much of it in the outer layers of the planet, the ones that cool down to form the crust. But over millions of years, as the planet had already begun to cool down and form a crust, there was an intense bombardment of meteorites. These meteorites are thought to have brought a substantial quantity of the water we have on Earth, as well as iron that remained trapped close to the surface, close enough to be accessible today. Iron was, and still is, by far the most abundant metal in the Earth's crust, but it was not the first to be discovered and used by humans, probably because it was harder to work than with copper. The first metals used for tools, weapons, and crafts were copper alloys, like bronze, which is copper and tin, or brass, which is copper and zinc. Hence the name Bronze Age. Bronze is an alloy and not an element. Actually, the term bronze is a bit imprecise. It can be used for any alloy that contains copper, and to a lesser extent, tin. But why was copper used long before iron? Because extracting a usable metal from iron ore requires furnaces that reach at least 1500 degrees Celsius or 2700 degrees Fahrenheit. This is 500 degrees Celsius or 900 degrees Fahrenheit higher than what is required to smelt copper. That's a huge difference, hundreds of degrees. This technical barrier to the use of iron is why the Bronze Age lasted for centuries, even thousands of years, before bronze was displaced by iron towards the end of the second millennium BC in Eurasia and later in other parts of the world. The importance of iron since then has never decreased, and iron is by far the most common metal in our daily lives, in building materials, almost all appliances, tools, cutlery, cars, and in particular in the form of steel. It is everywhere. Iron is also the cheapest of all metals due to its abundance and the size of the iron and steel industry. It costs only a few dollars per kilogram or per pound, which makes it cheaper than many foods by weight. That's a huge contrast with pre-industrial times, when it was not a precious material, but it was still rare and costly enough for people to take great care of whatever iron objects they owned. In the previous story, I told you that the very first element, apart from hydrogen, helium and lithium, with 1 to 3 protons respectively, appeared in stars as products of fusion between hydrogen nuclei. Elements 4 and 5, beryllium and boron, are a bit particular because they don't really form by the fusion of nuclei. They would not remain stable, but instead appear through the bombardment of existing nuclei by free protons. There are relatively few of these two elements. For that reason, they are not produced on a large scale. But if we leave them aside, after that, element 6, carbon, to 26, iron, are fused in stars. When they approach death, they have exhausted their hydrogen and helium reserves, and they fuse heavier atoms in the last years or moments of their lives as they approach their final burst in a supernova. But not all fusions are exactly the same. I told you about that in more detail in previous stories about nuclear fusion and astrophysics. The fusions that produce atoms up to 26 protons, up to iron, release energy when they happen. They are called exothermic. The energy needed to keep the new atom together is less than the energy needed to keep its predecessors together. In other words, it requires less binding energy. So when the nuclei fuse, this excess energy is released. But above 26 protons in the nucleus, fusion reactions become endothermic. they need to absorb, to consume energy that is turned into binding energy. So no star could ever live for long on the fusion of these two heavier atoms. Their creation, their appearance, happens only in the very last moments of a star's life, when considerable energy is released at once and can be absorbed to fuse these heavy elements. So iron is the last element in the periodic table whose formation by fusion is exothermic. The general rule is that the heavier an atom is, the more particles it contains, and the rarer it tends to be. As a broad general rule, it works. As we saw, there are incomparably more hydrogen and helium atoms, the first two elements, than any others in the universe, as far as we know. But the decrease in the abundance of elements with increasing mass is not perfectly linear or regular. I told you before that light elements like lithium or boron were relatively rare despite their small atomic number. This is because of their instability and the way they are created. The abundance of an element also depends on its binding energy, the quantity of energy it would take to make its nucleus break apart and become atoms of a different element, or an isotope of the same element if it gains or loses neutrons. Iron and its vast isotopes have one interesting characteristic. They have the highest binding energy among the thousands of different isotopes we know of. Thousands of isotopes because there are 118 elements, as we mentioned, and each of them has different isotopes, observed or theoretical. So that makes thousands of possible combinations. Out of all of them, iron atoms have the highest binding energy, which we could translate by saying that iron nuclei really prefer to stay the way they are. They are not inclined at all to break apart. This is thought to be a major reason behind the abundance of iron in the universe, despite its atomic number of 26. It is not such a light element, but once iron appears, it does not go away easily. Iron nuclei do not break apart easily, nor do they readily participate in the fusion reactions that create heavier elements. This means that over time, iron tends to accumulate in the universe, and its share of total matter increases. Number 27 is cobalt, a metal that was discovered in the 18th century. A little trivia about cobalt. The name cobalt comes from the German word kobold, which means goblin, one of the little creatures of folklore. But why call it goblin? Because ore containing cobalt seem rather useless and toxic to miners. It was poor in known metals that could be exploited, and when smelted it produced fumes containing arsenic, another element we will talk about later. These fumes were very toxic. In 1735, these cobalt ores were found to be the source of a new metal previously known, and it was named after this cobalt word. Cobalt was the first metal discovered since ancient times, after more than 2,000 years without the discovery of a new metal. Nowadays, cobalt is essentially obtained as a byproduct of the mining of more important metals like copper, but it has several uses in industry, particularly in alloys, and one that is very old, dating from before it was identified as an element. Cobalt in compounds like cobalt silicate or cobalt aluminate gives a deep blue color to paints, glass, and ceramics. These cobalt blue pigments have been used since antiquity in paintings, jewelry, and glass. In biology, cobalt is also an important component of vitamin B12, which is essential for all animals for cellular metabolism and DNA synthesis. Let's continue with element 28, nickel. I told you before that a large part of the iron in the Earth's crust is thought to have come from meteorites during the final stages of Earth's formation, when it was heavily bombarded. The same applies to nickel, and this meteoric nickel is often found in combination with iron. The main use of nickel is in metal alloys to improve their resistance to corrosion, or in plating. For the same reason, nickel is widely used in coins, for example. One particularity of nickel is that it is one of only 4 elements that are ferromagnetic at room temperature. The other 3 are iron, cobalt, and a rare element called gadolinium, one of the rare earth elements we talked about before. Ferromagnetic means that they can be attracted to magnets. We are going to conclude for tonight with element number 29, copper, another major metal and probably the most significant industrially after iron. Copper is a rather soft and malleable metal that has a very high thermal and electrical conductivity at room temperature. So it is the material of choice for electric cables, or more anecdotally for cookware, because heat spreads quickly through a copper pan or pot. It melts at about 1,000 degrees Celsius, a significantly lower temperature than iron. Another thing that made its use easier for our ancestors during prehistory is that it can sometimes be found in a directly usable metallic form, what is called a native metal, one that is found free and immediately usable, as opposed to being mixed with other elements in an ore. But the bulk of copper on Earth is found in copper ores, and it was also the first metal to be smelted from ore, around 5000 BC, thousands of years before iron. But because of its softness, pure copper is not very useful for tools or weapons. The first metals that were practically used on a large scale were bronze, that is to say, alloys of copper and tin. Copper in the Roman era was mined, in particular, on the island of Cyprus, and this is where the name copper comes from. The metal was later named cuprum in Latin, which eventually became copper in English. Nowadays, the major copper-producing regions are South America, especially Chile and Peru, the southern part of Africa, China, and the United States. It seems that copper still has a bright future ahead of it because of the transition toward even greater use of electricity to replace fossil fuels. This requires transmission infrastructure and should sustain demand for copper, which remains the only affordable and efficient option for most electrical cables. For mammals like us human beings, copper is found in very small quantities in our bodies, but for some mollusks and crustaceans, It can replace iron in blood cells. Our blood cells and those of fish use hemoglobin, which is a protein containing iron that facilitates the transport of oxygen in red blood cells. But some invertebrate animals do not have hemoglobin, but hemocyanin instead. These proteins can also bind oxygen temporarily to transport it, but with copper atoms instead of iron. This is why blood is not necessarily red. The blood of octopuses or horseshoe crabs is blue because of hemocyanin. We have covered many of the most familiar elements at this point, but we still have almost 89 to go. We will continue next time, starting with element number 30, zinc. We have come to the end of our little journey tonight. I hope you enjoyed this adventure, and I invite you to discover and learn more. Now you can let go and sleep. Or, if you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.